So the next talk then will be by Bethany Ehlmann, and she will talk about the Lunar Trailblazer.
Okay, thanks, folks. So some of you have seen this presentation before, but I'm going to actually focus on things that are the topical areas of this workshop as I talk to some of the slides. So next. So Lunar Trailblazer, as you're aware, many folks on the line are aware, we're a selected mission selected in June of 2019 under the Simplex competitive call that was open to the planetary science across the solar system with small satellites. We're jointly funded by PSD and SCO and are heading toward our preliminary design review in KDPC in October and November of 2020. We are currently slotted to go on NASA as mission IMAP, so thrilled to have that slot in 2024 to make our way to the moon as an ESPA Grande small sat. Lunar Trailblazer's goal is to understand the form, abundance, and distribution of water on the moon in the lunar water cycle, so very much in the topical areas of this workshop. Our first two objectives really focus on the sunlit side of the moon. So the things we want to measure with Lunar Trailblazer are the form, abundance, and distribution of water, meaning the form, distinguishing OH versus OH in minerals versus H2O. Okay, so form, abundance, how much, and distribution, and then whether it's time varying in terms of the mobility, and those will measure as a function of latitude, soil maturity, and lithology. The other thing, and most directly relevant to the topics of this workshop, are the form and abundance of ice versus bound H2O and OH in the permanently shadowed regions, perhaps resolving some of the questions that Paul was pointing out in his talk, using terrain scattered light to see what is at the surface. So Lunar Trailblazer is a surface sensing satellite in terms of our direct detection of water, and then we'll of course get thermophysical properties, objective 4, to understand how gradients and albedo and surface temperature influence the locations where we see ice and then bound H2O and OH. Along the way, I mean, we're going to get some awesome maps of geology for composition in terms of lithology. Those of you who are also fans of igneous petrology will be getting better spectral resolution than M-cubed and Diviner Force, the kind of next set of measurements and refinements of igneous composition, and being able to do recon for some of the landed missions we're talking about. Go to the next slide. We do this via two instruments. So an imaging spectrometer, HVM cubed, which has heritage from M cubed and then was miniaturized under a Picasso. So you can see the tech specs there, less than 70 meters per pixel, a spectral range that includes the full water-related vibrational absorption at a 10 nanometer spectral resolution, and then the lunar thermal mapper, these data sets are co-nested, so we get even higher resolution thermal pixels for composition and temperature within the HVM cubed pixels, where we're sensing water from reflected infrared light at the surface, and the simultaneous thermal mapper enables us to correct the data. So if we keep going here, you can see, so I don't usually talk about this at talks, but this is an audience that cares about water. And so we have performance requirements that are set by these low signal regions in the PSR, okay, where we most expect to find the water and the volatiles. So what you're seeing here on the little graphic on the right is the difference between water ice, which is in red, and water just bound, which is in blue. And so our performance requirement is set not just by detecting ice, but actually detecting ice and discriminating it from mineral bound water, which is really crucial for understanding the resources question and also scientifically understanding what's there. And so you can see that difference if you then convert that and bring that through a model for radiance using terrain scattered light off the shadows. This is our artist concept on the left. The difference there is a part per 10 to the 5th, but you can see we have a lot of margin against, in our current performance estimate, the middle graphic there, the margin against our current performance according for what's required to do that discrimination. So if we go to the next slide, our baseline is that we're collecting targeted data of the moon in select locales relevant to those of you who are going into breakout sessions, we'll be presenting NASA with the results of a phase A/B study that will explain to NASA what it would take, basically a small upgrade in the comm system to get global coverage, but we'll be getting good coverage in the PSRs and a number of targets next. And I'll conclude by saying that in terms of addressing the workshop questions about which volatiles are present, how do we identify high priority samples, and how do we collect them, Trailblazer will supply spatially resolved maps of H2O ice versus OH H2O at less than 500 meters per pixel. We'll have a spectral range that enables us to also see organics, CO2, CH4, what's listed there, if it is there, and thermophysical properties of the surface at less than 50 meters. So I'll leave it there. Thanks.